All right, solutions for problems 45 to 53, odds, from Chapter 10. These are problems about torque. I'll just remind you here that torque is the rotational analog of force, and we calculate it. Force times radius times the sine of the angle between them. So you get no torque. If the angle between them is 0, then you get no torque. This is 0. If they're perpendicular to each other, 90 degrees, then you get maximum torque. This is 1. It's just force times radius. Number 45. I'm not going to redraw that lumpy looking thing there. I will say right off the bat here that you have to pay attention to a torque can make something want to rotate clockwise or counterclockwise. And torques will fight against each other just like forces can fight against each other if they're trying to make something rotate in opposite directions. And you have to pay attention to that. So in this case, right off the bat, I can see that force 1 and torque 1 is going to try to make this object rotate in the counterclockwise direction. The convention you can choose, just like in kinematics problems say, you can choose the positive direction to be whatever you want. The conventional choice here is that counterclockwise is the positive direction. Why do we choose that? Because that's how we measure angles, right? We measure angles going around this way. So that's what we think to be the positive direction. You don't have to do that, but that's the usual choice, just like usually we choose up to be positive, for example. So T1, the torque caused by force 1, I'm going to call that a positive torque. The force is 4.2 newtons times it's acting at a radius of 1.3 meters, and the angle between them, if you imagine both of those vectors like hands of a clock coming from the same point, and that little theta 1 is the angle that we want. The sine is 75 degrees. That's positive torque. I'll calculate that in a second. Torque 2 is trying to make it rotate in the opposite direction, which I will call the negative direction. So it's going to be a negative torque. It's going the other way. And I think that that's something you can just do by looking. I mean, you can just tell what direction they're going to rotate, right? If you just imagine force 1 all by itself, or force 2 all by itself. This one is 4.9 newtons times radius is 2.15 meters, and the angle between those is 60 degrees. I'll calculate those now. Make sure that I'm in degree mode. I'm not. Alright, so I've got 4.2 times 1.3 times the sine of the angle between them. So that's about 5.27. And that's newtons times meters. Those are the units for torque. If you're thinking to yourself, hey, newtons times meters, that's joules. Well, yeah, it's equivalent to joules, but in this case, when we're talking about torques, it doesn't really make sense to equate that to the units of energy, so we leave them as Newton meters. And here, this one we've got 4.9 times 2.15 times the sine of the angle between them. That's 9.12, and that's torquing the other way. Trying to get it to rotate the other way. So the total torque is 5.27 minus 9.12. Whoops. Let's try that again. 5.27 minus 9.12 negative 3.85 Newton meters. And there weren't any negatives in the problem, so I would say that it's 3.85 Newton meters clockwise. Let's see how the book reports that. Oh, they do give it as a negative, so either way. But that's what the negative means, right? Number 47. Small ball of mass 0.75 kilograms is attached to one end of a 1.25 meter long massless rod, and the other end of the rod is hung from a pivot. When the resulting pendulum is 30 degrees from the vertical, what is the magnitude of the gravitational torque calculated about the pivot? So, got a rod, the ball on the end of it, and the mass of this is 0.75 kilograms. The gravitational force, of course, would be straight down, just be mg, and the radius is this, right? That's the pivot, so this is the radius. The r is the distance from the pivot. That r is 1.25 meters. And if you imagine those two things as the hands of a clock, that would be here. The angle between them is 30 degrees. So the gravitational torque just means the torque caused by gravity, is the gravitational force times the radius times the sine of the angle between them, which is mg, that's my gravitational force, times r times the sine of the angle between them. Sine of 30 is just 1/2. So that is 0.75 times 9.8 times 0.25 times the sine of 30 is 1/2. So that is a torque of 4.59 Newton meters. That torque from gravity is going to make this one go, it's going to make it rotate this way, right? And that would be in the clockwise direction, so that's the negative direction. So we could call that a negative torque. Let's see if the book did that. They did not in this case, so I think that's a little bit inconsistent. Or maybe they said magnitude. Did they? Yeah, they said magnitude, so that's why they dropped the negative. But we could call, if we were following the convention that counterclockwise is positive, we'd say that that's a negative torque. They asked for the magnitude, so you ditch the negative sign. All right, so that's how you calculate torques. The next few problems are based on Newton's second law in rotational form, which is that net torque is equal to moment of inertia times angular acceleration, and that is the parallel of this, right, with all the rotational analogs. Beautiful that that works, don't you think? All right, so 49. During the launch from a board, a diver's angular speed about her center of mass changes from 0 to 6.2 radians per second in 220 milliseconds. So that sounds like kinematics, doesn't it? So she goes from 0 to 6.2 radians per second in a time of 0.22 seconds, which means her angular acceleration, if I use the equation then her angular acceleration, that's 0, right? So it would just be 6.2 divided by 0.22, which is about 28 radians per second per second. We need that. her rotational inertia about her center of mass is 12 kilogram meters squared. They want to know during the launch what are the magnitudes of her average angular acceleration, which we already found, so that's the answer for part A right there. And the average external torque on her from the board, so that's just the torque, right? They mean external torque as in, not as in like whatever her muscles are doing internal to her body to cause her body to do different things. We're talking about the external torque to her body. So torque is equal to I alpha. So in this case, that is 12 kilogram meters squared times 28 radians per second. And that will give us, you can check to see the units that are dimensionally consistent. They are. It will give us 12 times 28, about 336 Newton meters of torque on our diver. Cool. Oops. Recycle the other half of that page. What am I on now? So that was number 49, right? So 51. Looks like an Atwood's machine. But this time, more realistically perhaps, the pulley is not frictionless. I guess it is frictionless, but it's not massless. So that means we have to take into account the what's happening with the pulley. So let's see what we have here. We have, I'm just going to copy, I think it will help me to have this here. There's R, and then on this side I have M1 and M2. And since the pulley has mass, that means the tensions are not the same. They are not the same. Which they were the same in our old Atwood's machine problems because we assumed the pulley was massless, but now they are not the same because the pulley has mass. So when released from rest, block 2 falls 75 centimeters in 5 seconds without the cord slipping. So 75 centimeters it falls that much in how long? 5 seconds? And it starts from rest. So I need to find the acceleration here. And I can do that using delta y equals 1/2 at squared plus vit. The vi is 0, so it's just this. And I can find the acceleration would then be equal to 2 delta y over t squared, which is 2 delta y over t squared. So the acceleration is about 0.06 meters per second squared. Let's see if that is in fact the answer for part A, isn't it? That's what they were asking for there. And what else do they want to know? What are the tensions T2 and T1? And then what's the magnitude of the pulley's angular acceleration, and what is its rotational inertia? All right, so that's our answer for part A. Part B. B and C, we want to find the tensions. So there's a bunch of equations here that we need to write. We need to write the net force equation for each pulley. And let me just write their masses in here so I know which way it's going. Mass 1 is 0.46 kilograms, and mass 2 is 0.50 kilograms. Right? So it's going this way, which means that on mass 1, the sum of all forces on mass 1, that's going up So that means T1 is winning versus gravity. And net force is on block 2. Block 2, gravity is winning. Right, so those are my net force equations for each of those. Now, let's see, mass, net force is equal to mass times acceleration. So the mass of this block is 0.46, the acceleration is 0.06, found that here. That's equal to T1 minus M1 times G. So I think that's going to give us T1, right? T1 is equal to this plus this. So that's 0.46 times 0.06 plus 0.46 times 9.8. So that's about 0.1, no, I'll say 0.124 newtons. And then I guess that's the answer for part B. Uh-oh. That doesn't look like what they have there. Let me just check my work here. Looks like I have the answer to part A right. So what did I do here? So mass times acceleration. Oops, I multiplied there. I see what I did, sorry. You probably saw that before, didn't you? I multiplied here instead of adding. Sorry. There we go. So scratch that. It's 4.54 newtons. And then T2, we have to do the same thing. So this is part C now. Mass times acceleration equals mass times gravity minus T2. So that's going to be 0.5 times 0.06 plus, oops, sorry, check that. So T2, I move that over here, it's going to be 0.5 times 9.8 minus 0.5 times 0.06. And that's 4.87. newtons. And then, finally, in part D, oh sorry, there's an E too. What's the magnitude of the pulley's angular acceleration? Well, I know that linear acceleration is equal to alpha times r, right? And the linear acceleration of the rim of the pulley is the same as the acceleration of these, right? Because the rope is not slipping. This is true if it's not slipping. If it is slipping, then that relationship would not hold, right? Because the blocks would actually be moving a little bit faster. They would have a greater acceleration than the rim of the pulley. But if it's not slipping, and they did say that, then this relationship would be true. So that means that my angular acceleration is equal to a over r, which is 0.06 over the radius, which was 5 centimeters. So that's 1.2 radians per second. Right? And then last part, now that we know all that, what's the rotational inertia of the pulley? Well, I know that net torque is equal to I times alpha, right? Now there's two torques on this pulley. There's the torque from tension 2 and a torque from tension 1. they're both trying to make the pulley, and they're both down, right? As far as the pulley is concerned, this rope's pulling down this way, this one's pulling this way. So those torques are fighting against each other. T2 is winning, right? So the net torque is the torque from T2, which is T2 times the radius. And notice, this is always true for pulleys and things like this, notice that this is coming off at a 90-degree angle. So that sine theta is going to be just equal to 1. That's 90 degrees on this side, so is it here. Doesn't matter where the rope would be pulling off, it would always be pulling off at a 90-degree angle. So my net torque is the torque from T2, which is T2 times R, minus the torque from T1, which is T1 times R. That's equal to I times alpha. And I know all of these things except for I, so I should be able to solve for that. So I is equal to T2 times R minus T1 times R all over alpha. All right, let's see if we can do that then. So T2, 4.87 times R, what was the R? 0.05 minus T1 times R, all divided by alpha. Alpha was 1.2 radians per second per second. So the moment of inertia of our pulley is 0.138. Oops, sorry, there's a 0 in there. 0.0138 kilogram meters squared. That is the rotational inertia of the pulley. How about that? Pretty cool. And is it the last one, or am I doing one more for you? We're doing up through one more, 53. Then it's time for bed. 53. So we got a figure here. There's two torques. They're fighting against each other again, playing at this disc. It shows a uniform disc that can rotate around its center like a merry-go-round. Disc has a radius of 2 centimeters and a mass of 20 grams. And it's initially at rest. Starting at time 0, two forces are to be applied tangentially to the rim. So tangentially, that means our sine theta will be 1, sine of 90 degrees, as indicated, so that at time t, 1.25 seconds, the disk has an angular velocity of 250 radians per second counterclockwise. So counterclockwise, positive direction, which means that F2 is winning, right, versus F1. The torque caused by F2 is winning against this torque. Let's do the kinematics here to figure that out. So they say it's starting from rest, and then at how much time? 1.25 seconds later, it's going to have an angular velocity of 250 radians per second. Right. So that means the angular acceleration, you can set up that equation. The initial is just 0. So that means our angular acceleration is just that divided by that, 250 divided by 1.25, or 200 radians per second squared. And they want to know, they gave us one of the forces, they want to know the other one. So I know that net torque, that's an ugly looking sigma, that net torque is equal to I alpha. Right? And they told us that this is a uniform disk, so that's a 1/2 mr squared. Right? That's our moment of inertia. Now, there are two torques here, and we know that since it's rotating this way, that F2 is winning. So that means F2R minus F1R, those are my torques, torque 2 minus torque 1 is equal to I, which is, let me fill that in, 1/2 mr squared times alpha. And I think I know everything in this equation except for F2, right? And that's what they want me to find. So let's go ahead and fill everything in that we know. So F2 times the radius, 0.02, minus F1 they told me is 1/10 of a Newton, 0.1, times the radius, 0.02, is equal to 1/2. The mass of the disk is 0.02, times the radius of the disk is also 0.02 squared, times alpha, which we found here, is 200. So I think what I'm going to do is leave that there, and then I'll calculate this and add that over to the other side. So I've got 1/2 times 0.02 times 0.02 squared times 200. Then I have to add this over to there, 0.1 times 0.02. And then divide by 0.02. And I get that that force has a magnitude of 0.14 newtons. And we were certainly hoping that it would come out to be something a little bit bigger than F1, because we knew that it was winning, and it did. Yay! So there you go. That's how you work with Newton's second law in rotational form.